Hello everyone, welcome to all in this lecture. So in the previous 4 lecture, I have discussed some GATE previous year questions from the bearing capacity of soil topic. So in this lecture, I will discuss CRS strength of soil, some GATE previous year question from the CRS strength of soil. Or in the coming lecture also, I will discuss uh, some more numerical problems from the GATE previous year question for the shear strength of soil topic. So let's start. So the first question, we have the state of stress represented by Mohr circle shown in the figure, and we have to choose the option according to this. So let's discuss. First, let's discuss what is the Mohr circle. So Mohr circle is the graphical representation of normal stress and shear stress. If you want to calculate uh, normal stress and shear strength at any point, suppose this is the given, okay, and there is acting different normal stresses, sigma x, and you want to calculate at this plane, that is angle theta with the horizontal, and at this place you want to calculate sigma and tau. So Mohr circle, suppose this is the Mohr circle that is drawn on the sigma and tau axis, that is tau axis on the vertical direction, or you can say shear axis also on the y direction, and we keep normal stress in the horizontal direction. Okay, so every point of this curve or this Mohr circle will give us the normal stress and shear stress. So how we can get, suppose this is the center of Mohr circle, so we can go rotate 2 theta from the horizontal axis from the center. So this point, suppose P, will give us the normal stress and shear stress on a plane which is inclined at an angle theta to the horizontal axis. Okay, so construction procedure I'm going to discuss for two cases. Case one, we have, suppose you have given this sigma x, sigma x, sigma y, sigma y, and we want to calculate this plane normal stress and shear stress. So how we can calculate? So by drawing a Mohr circle. So first, keep the tau shear stress on vertical axis and keep the normal stress on horizontal axis or x-axis. So suppose in this case sigma x is greater than sigma y. So first locate the sigma x, and we're taking the sign convention. What is the sign convention? We are taking the sign convention. Compressive stress will be positive and tensile stress will be negative. Taking this sign convention, we are going to draw this. So locate the sigma x. Let's assume somewhere here. Then draw. Then locate the sigma y, and we have taken the sigma x is greater than sigma y. So by draw a line and find the midpoint of this line. So here it would be somewhere. So this would be the center of Mohr circle. By taking this radius, we can draw Mohr circle like this. So this is called Mohr circle. So we want to calculate the sigma and tau, and location of every point of this Mohr circle will give us the normal and shear stress. So we want to calculate at an angle theta, at a plane at an angle theta with the horizontal. So what we have to do, we have to go rotate here to 2 theta, which we get this point. So coordinate of this point will give us the normal and shear stress at this plane, right? So this is the main procedure. So in this case, center would be what we can write center sigma x plus sigma y divided by 2, 0. Y coordinate is 0, right? And what would the radius? Radius would be sigma x minus sigma y divided by 2. Okay. Now discuss. I'm going to discuss for second case. So in the previous case, I have seen that this. In the previous case, I'm going to discuss second one also. Second one only. So we have seen this is the sigma y, and this is the sigma x. Okay. So in this case, we will see the shear stresses on this plane and on the horizontal plane and on the vertical plane. There is a shear stress is 0. So when shear stress is 0, we call that plane as a principal plane. Okay. And whatever the normal stress acting on that principal plane, we call as a major principal stress and minor principal stress. Major one we denoted by sigma 1, minor one we denoted by sigma 3. Minor principal stress. Okay, so in this case, we can say sigma 1, if you are assuming the sigma 1 x greater than sigma x is greater than sigma y. So you will get the sigma y, sigma 1 is equal to sigma x, and this is a major principal stress. Similarly, sigma 3 is equal to sigma y, that is minor principal stress. Or by drawing the Mohr circle, you can see here, what is the coordinate? Here the coordinate is you will get 6 sigma x and y coordinate 0. It means shear stress here is 0. So this will be the major principal stress. Here also you can see there is a coordinate sigma y and 0. Here also the shear stress is 0. It means sigma y is minor principal stress. So by drawing the Mohr circle, wherever you will get the shear stress is 0, you can say this is the major or minor principal stress. So greater value will be the major principal stress, minor value will be the minor principal stress. I get your point. Okay. So now we can go to discuss second case. So the second case we have, suppose in the second case, I'm going to give some shear stress also. So in that case, how we can draw the Mohr circle. Okay. And here there is a shear stress also. That is tau xy. Okay. So now in this case, I'm going to calculate at this angle theta, what will be the normal stress and what will be the shear. Okay. So this sigma x and sigma y, this in this case, they are not principal stress. Okay, because here tau xy is 0, hence shear stress is not 0 in the vertical plane or horizontal plane. Okay, so we will find also what will be the normal principal stress and major and minor. So let's go to calculate, or let's go to draw a circle for this case. So first locate the shear stress on vertical axis and locate the sigma stress or sigma axis on the x-axis. Sigma, there is normal stress on the horizontal axis. Okay. Now, in this case also, there is just assumption that compressive stress is a positive, tensile is a negative, and there is other. When you are seeing this condition, so the shear stress will be positive. When you are seeing a opposite condition like this, you will say negative for the shear. So in this case, what will happen? You will see. Suppose this is the block. I'm explaining in the block direction in the by showing some blocks. So this is shear is happening, and that this block is angle is get reduced. Angle is get reduced. We'll see there is a first it was 90 degree, then it's reduced by theta. So that is called the if we'll in this case we will take a positive, and when will this will get increased, in this case will take a negative. Okay, so in this case also assume sigma x is greater than sigma y. Okay, so suppose here I'm writing sigma x, here I'm locating sigma x, and here I'm locating sigma y. Okay, so what we have to do, draw a perpendicular line and cut equal to tau xy. Here also draw, but it should be in opposite direction. You can draw here also in one direction and here in the downward direction. So I am drawing here at a point of sigma x in a vertical upward direction. Here you have to draw in a vertical downward direction equal to. So this 2 point we will meet. So this will be the center of Mohr circle, and this would be the radius. Okay, so by taking the center this radiusly, we can draw the Mohr circle. Okay, you can correct like this. So see, every point of this Mohr circle will give us the normal stress and shear stress that we know. See, at this point, what is that? There would be some normal stress, but shear stress is 0. Means this stress we can call a major principal stress. So that I am writing sigma 1. See, at this point, what will be shear stress? That is 0. Shear stress is 0. So this, whatever the normal stress in this point would be the minor principal stress. So I'm writing sigma 3 0. So in this case, you can see sigma 1 is greater than sigma x. In the previous case, sigma 1 was equal to sigma x. So this, so sigma x is here, sigma 1 is here. Okay. So now, and now we can draw a, suppose we are going to find theta. So we have to rotate from 2 theta from this axis, not horizontal axis, from this axis, right? And suppose it will cut this Mohr circle up at this point. So this is the P point. So whatever the normal essential stress will get at the P, it will be give us the normal stress and shear stress at an angle, at a plane, at an angle theta with the horizontal. So now we are very clear about this. So I've shown the what is the construction procedure and how we can locate how we can calculate the shear stress and normal stress at a various particular plane by drawing the Mohr circle. So now let's come to our question. What is that? So now we have the very brief idea about the Mohr circle. There is other important characteristics about Mohr circle also, but I have not discussed because I have to solve this question. I'm whatever it was required, I have discussed that only. So first case, there is hydrostatic condition. It means there is a compressive sigma normal stress is acting from the all around. So this is the case. So let's draw the Mohr circle for this case. This is the tau, this is the sigma. So sigma x is here, suppose somewhere here. Sigma y is also some here also. So you can see sigma x and sigma y coincide. So Mohr circle will say, in this case, Mohr circle is a point at a distance sigma from the origin. So according to this figure, option is not correct. Let's discuss the B. Uniaxial tension. Uniaxial tension means a tensile stress is acting, suppose sigma, in a one direction. Either you can draw in this direction or you can draw in this direction. So I'm writing this. So now we can go further drawing this. Okay. See, in this case, sigma x is not given, it means 0. Okay. So This is the x is tau, and this is sigma. So this is now we got the one point, that is sigma x, that is 0. This is the sigma x. Now sigma y, that is in tensile. Tensile we take in negative. So it will come somewhere here, somewhere here, right? So that is minus sigma. So this is sigma y. So these 2 points, we got the center, then we can draw the Mohr circle. Okay. So by seeing this figure, also we can say option B is not correct. Now option C, biaxial tension or equal magnitude. This is the case. Biaxial means in a both direction, and magnitude are same. So it means we can say tension sigma, 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 sigma. So let's draw the Mohr circle for this case. Tau, sigma. Here sigma x is minus, so it will come somewhere here. Because tensile, I'm writing minus. Sigma y is also here. It will coincide. So in this case, we can say Mohr circle is point at a distance of minus sigma. Mohr circle is point at a distance of minus sigma from the origin. So we can say by checking this, by seeing this figure, option C is also not correct. Now, option D, pure shear. It means this is the case. You can see there is no normal shear acting, only shear acting. So this is the tau. Tau. What is the construction position? First draw the sigma. First look at the sigma x, and that is not given, means 0. Sigma x is here. Now look at the sigma y, that is also 0. Say here. So from the sigma x, draw a vertical line, that is tau. From the sigma y, that is also here, so you would draw a line tau. Hitting this point, this will be the center. So in this case, we can say origin. Origin is a center of a circle, of a Mohr circle. Center of Mohr circle. Okay. So by checking this figure, we can say D option is correct. D option is correct. Now let's go for the next question. In a drain triaxial compression test, a sample of sand fails at a deviated stress 150 kilopascal under the confining pressure 50 kilopascal. The angle of internal friction phi in degree rounded off to the nearest integer, the sample is. So I'm going to discuss some short. I'm giving some short idea about this triaxial test. So in triaxial test, there is a cylindrical sample, and what we do first, we give some confining pressure, that is sigma 3, sigma 3, sigma 3, sigma 3. After that, we give some deviated stress sigma d by applying from the jack, from the machine. We give some extra pressure, we apply some extra pressure from the vertical direction. Okay, so again some pressure acting, sigma d. So you will see there is no shear stresses on the plane, on the vertical horizontal plane. So in this case, you can see whatever the pressure that is coming on the vertical direction, that is major principal stress, and that will be equal to sigma d plus sigma 3. And here is the sigma 3 also equal to confining pressure. Sigma c is a confining pressure, or also we can call sail pressure. And there is a relation between sigma 1 and sigma 3, that is 10 is sigma 1 is equal to sigma 3, 10 square, 45 plus 5 by 2 plus 2c, 10, 45 degree plus 5 by 2. So this relation is very important when you are working in triaxial test, right? Okay, where phi and c are the shear strength parameters for soil. Okay, so now we can go for to solve these questions. So now we can easily understand because we have some idea about the triaxial compression test. So here you can first thing is mentioned sand, and there is a sigma d is given 150 kilopascal. Cell pressure, that is sigma c or sigma 3, is given 50 kilopascal. Okay, so and sand is given. Sand means c is equal to 0, positionless. So by putting the c is equal to 0, this expression will be 0. So finally we can write sigma 1 is equal to sigma d plus sigma 3 equal to sigma 3 10 square 45 degree plus 5 by 2. So we'll get 150 plus 50 is equal to 50 10 square 45 degree plus 5 by 2. So we'll get 45 plus 5 by 2 is equal to 2. By solving this, taking the sign inverse, we will get 5 is equal to, I've calculated that writing directly over here, 36.86 degree. Okay, let's go for the next question that we have. Okay, this is a very important question. For a plane stress problem, state of stress at a point is represented by the stress element shown in this figure. Shown in the figure. By how much angle theta in degree the stress element should be rotated in order to get the planes of maximum shear stress. So we will say in this case, like suppose this is the problem given, and somewhere else I am writing this is the plate and here is sigma max. Okay, shear max is given. Okay, and suppose this angle is somewhere alpha from the horizon. Okay, so the question is saying the how much angle in degree the stress element should be rotated to get the maximum principal plane. So suppose we are starting rotating. So theta should be equal to alpha to get the plane of maximum C, because the maximum C is at an angle alpha with the horizontal. So we have to calculate alpha. It means we have to calculate uh, at a plane at an angle of a plane maximum shear stress with the horizontals. We have to calculate alpha in this case. So how we'll calculate? So for this kind of problem, there is a general expression for shear stress that I'm writing over here. So that will be equal to sigma y minus sigma x divided by 2 into sine 2 theta minus tau xy cos 2 theta, right? And this is this expression, general expression for this case. So you have to understand this also, where sigma y, sigma x, sigma. In the second case I have discussed in the previous slide, sigma x, and there is a tau xy. So this expression for this case, okay? So I will put the value according to the sign convention. So shear stress is equal to this. So now we can find that if the shear stress is maximum, then what angle will be? What value of the theta? So that we can calculate by using the mathematical rules, mathematical some rules like first differentiate tau with respect to theta. So what we will get? This is the constant value, so we can write sigma y minus sigma x by 2 sine 2 theta into 2 minus tau xy is also constant quantity, we can take outside, minus sine tau cos 2 theta differentiation sine 2 theta into 2. So now we can equate 0 to get the maximum shear stress and to get the theta. So what will be the theta? So by equating you can get this minus minus plus. So we can get, writing directly, you can calculate tau xy minus tau x minus tau y. Sorry. Sigma x minus sigma y divided by 2 tau xy is equal to 10 to theta. This theta we can say for maximum shear. So always remember this equation to get theta for the maximum shear stress. So no need to derive all the time. Okay, so I've derived once. So you should remember, you have to remember this equation. Okay, now we can calculate theta. So 10 to theta is equal to here sigma x minus sigma y. Or according to the sum convention, put the value sigma x. Here you can see there's a tensile, so it would be minus 80. Sigma y, this is compressive, so it will be positive. You can write like this. Into see shear stress in the opposite direction. Okay, this direction we take as a negative. So here we can write minus 25. So what we will get 100 divided by 52. So theta you will get from this value theta will get 31.7 degree. Now you can check the option. So just remember this formula, no need to calculate, no need to derive all these things. Okay. From the second question, from the next question, whenever you get these types of question, always use this formula. So again, I'm repeating this theta, its angle of that plane with the horizontal for the maximum shear, maximum shear. Okay. So get the theta is equal to 31.7 degree. Okay, let's go for the next question that we have. A soil sample is subjected to a hydrostatic pressure sigma. The Mohr circle for any point in the soil sample would be hydrostatic pressure. Already I've discussed in the first question. This is the condition here. No, compressive. I'm writing it. Sigma. Okay, this condition. So we can draw the Mohr circle for this. So first look at the this is equal to sigma x, this is equal to sigma y, this is equal to sigma y, is equal to sigma x. First locate. So this is compressive nature, so it would be here. Now we can look at the sigma y also. Sigma y is also here. So we can say Mohr circle is a point in this case at a distance sigma from the origin. Now we can check the option. A circle of radius and center at the origin, no. A circle of radius center at the distance from the origin, no. At a point at distance from the origin, so option C is correct. A circle of diameter, no. So you can see option C is correct. Let's go for the next question that we have. In an unconsolidated, undrained triaxial test, it is observed that cell pressure is increased from this to 150 kilopascal to 250 kilopascal, leads to a pore water pressure increase 80 kilopascal. It is further observed that increase in the 50 kilopascal in deviatoric stress result in increase in the 25 kilopascal in pore water pressure. The value of Skempton pressure parameters be equal to. So let's discuss what is the Skempton pore pressure parameter, that is A and B. There are two parameters A and B. So I'm not going to derive all this relation, but I will give you the some sort of idea about the what is this A and B. So you will see when you will increase change in the pore water pressure by increasing the cell pressure. So there is a relation with the B. When you changing the cell pressure, pore water pressure will increase. So this is one relation. When you are changing the deviator stress, the pore water pressure will change. So this is the two relation are very important. So always remember this. Okay, now we can come to the questions like cell pressure are increasing from 152 or 150 to 250. So we can calculate change 250 minus 150, 100 kilo Pascal. Okay, and by increasing the sigma 3, water pressure increase, we can write delta Q3, that is 80, which given. Now, when you are increasing the derivative stress 50, in sigma U, sigma delta sigma D 50 kilopascal. So pore water pressure. See, here I'm writing D or D. It means you are working the derivative stress, the pore water pressure increasing. Here I'm writing 3 means we are working. We are increasing or decreasing in the cell pressure, then pore water pressure increasing. So there is notation you have to follow. So pore water pressure is 25 kilopascal when you increase the derivative stress. Now we can use the equation. So this 100 is equal to 80 is equal to B into 100. So B will get 0.8. Now 25 is equal to A into B into 50. So AB we can get 0.5. B we have 0.8. So A we can get 0.5 divided by 0.8. So we can get 0.625. So A, B, both we can calculate. The question is it is asking what is the B. So B it is 0.8. In the some other question you can see there is a we have to calculate A also, right? So these two relation are very important when you are working and when we are doing some operation for the pore Skempton pore pressure, right? B and A, right? Okay. So next question we have, you can see, consider the following statement related to the pore pressure parameter A and B. Okay, so pore pressure parameter I have already in the previous slide. So this is the relation, and this is the relation for temperature A into B. Okay, but you will see the graph also how it's changing. So I'm writing graph for the B, variation of B in the vertical direction, and there is a H percentage horizontal direction. And here S is the degree of saturation. Degree of saturation. Okay. So we'll see the graph like this. Okay. We'll see the graph like this. Like this. See like this. Okay. Okay. So we'll see here it's 1.0, here something here the 0. Like 0.8, you can write 0.6, 0.4, whatever. 0.2. And in this case here, 100, you can write 80, you can write 60, 40, 20. So we'll see when your S is equal to 100%, then B will be 1. And it will be constant when you're increasing the degree of saturation. When S is equal to less than 100, you will see less than 1. So you will see in this graph that B is going from 0 to 1. So we can say B is vary 0 to 1. You can put the equality sign also. Okay. Now for B, we got, so that's like 0 to 1. Now let's discuss what is the variation curve for the A. So here is the AF. I will tell you what is the AF, and here is the over consolidation ratio. Okay. So you will see the graph. It will come like this. So here you will say 1.0. Here you will see 0.5. Here you will say 0. And here we will see minus 0.5 something like this. So here from it will start negative. So you will see 4, 6, 8. So you will see when the over consolidation ratio greater than 4. So in this case, you will see AF is negative. AF is means we are going to suppose we are going to define the shear strength parameters. In this case, we will use the this Skempton pore pressure parameter or water pressure parameter. So what will happen when at the failure condition? So always you will say there is a relation. You have seen the relation A between the pore water pressure and between the levitated stress, or between the uh, levitated stress at a failure also. So when we are working on a failure, so we can call AF, right? There is a particular section we can say. At a particular stage, we can say when you're working on the failure, so we can write AF. So you can say when you are increasing, when the over consolidation ratio is greater than 4, say if in this case negative. And for the sensitive clay, AF can be greater than 1. So we can say AF can be negative, AF can be in between 0 to 1, it can be greater than 1. Now we can check the option. A always lies between 0 and 1, always lie, that is not correct. A can also be 0 or greater than 1, this can be correct. B always lie between 0 to 1, this is correct for B. So by checking this option, B can be less than 1, no, B cannot be less than 0 and greater than 1. So Q and R, so option C will be correct. Option C will be correct. Next question we have, the effective stress friction angle of a saturated cohesionless soil. Cohesionless soil means C is equal to 0, 38 degree. So phi is given 38 degree. The ratio of shear stress and normal stress at a failure plane. Failure plane we can write tau wave, normal effective. So there is a relation. You will see C plus tau wave C plus normal effective stress into 10 phi. 10 phi. So putting the value C is equal to 0, we can write tau wave. This is very question, and we can take the ratio also. 10 phi. So 10, 38 degree we can get 0.781. Option A is correct. Right. So this is a very easy question. But for this question, you have to be remember the relation. This relation C plus, that is cohesion of a soil, normal effective stress 10 phi. This is the angle of internal friction. This is the shear strength at failure. Shear stress or strength we can write. Okay, let's go for the next question. When tester is normally used to determine the in situ shear strength of, so it is for soft clay. You will see there is a blade, and we rotate the blades blade, we give the torque, and we will rotate the blade, and we assume there is a cohesion, and so it should be a soft, so that we can rotate by providing some torque. And we cannot use this stage for the stiff clay, right? So soft clay, option A is correct. This standard penetration test we use for the sand. Penetration test. Okay, so option A is correct. Okay, the unconfined compressive strength of a stiff clay fall in the range. So there is a table is we have this one. So by looking for this table, we can calculate stiff clay here. So unconfined ratio is strength is vary from 100 to 200. So option C is correct. So you have to remember this table. If uh, in next time it will ask for from the hard soil, medium clay, and soft type of soil. So what will be the range? And you can remember this also, consistency index. So what will be the consistency index, the range for the stiff clay? That is 75 to 100. So next question we have. Uh, in a drain triaxial compression test conducted on a dry sand, failure occurred when the deviated stress was 218 kilonewton per meter square at a confining pressure sigma C or sigma 3, we can say 61 kilonewton per meter square. What is the angle of shear resistance and the inclination of failure plane to the major principal plane theta P, or we can say theta F. So first write the general expression that we have. Sigma 1 is equal to sigma 3 10 square 45 plus 45 degree plus 5 by 2 plus 2c 10 45 degree plus 5 by 2. In this case, dry sand is equal to 0. So put c is equal to 0, we can get this expression sigma 1 is equal to sigma 3 10 square 45 plus 5 by 2. So we have the sigma, that is sigma 1 is equal to sigma d plus sigma 3. So we can write 2 1 plus 61 is equal to 63. 61 is equal to 61. Here is also sigma 3. 10 square 45 plus 5 by 2. So you can get 9. By solving this equation, you can get phi is equal to 40 degree. You get 40 degree. So now there is a relation between inclination of failure plane with the major principal plane to the angle of internal friction, that is 45 degree plus 5 by 2 is equal to theta F. So 45 plus 45 by 2 means 20 degree. So it will come 65 degree theta F. So check the option 65 40, option D is correct. Okay, so this relation is very important for the triaxial test, for the UCT test, unconfined compression test. In unconfined compression test, there is a sigma 3 is 0. So by putting the sigma 3 is 0, you can get the expression for unconfined compression test also. So next question we have. Write true false in this answer, in the answer book. If the Mohr circle for a given state of a stress lies entirely below the Mohr envelope for a soil will be unstable for the state of stress. So what is the Mohr envelope? Suppose this is the graph I'm making. The shear stress between vertical axis, normal stress would be on this sigma x axis. Okay, And suppose this is the Mohr circle, and this is the suppose this is critical combination where that Mohr envelope touch at the Mohr circle. So by drawing the line of different, by increasing the normal stress, you will get the shear stress. So we can calculate different point or different combination of critical combination of shear and tau. So by joining of the critical combination of shear of lines, so it will give some line, suppose like this. So that is Mohr envelope. What is the meaning of this? Suppose at this point there is some normal stress and there is a shear. So if you will apply by performing the test, you will apply this normal stress. So the soil will get fail at this shear. Soil get fail up to this tau shear. Suppose you are applying some different normal stress. Suppose this applying you applied some different normal stress like sigma 1, and this is the tau shear stress tau 1. So when you are applying now keeping the normal stress sigma 1, so soil will get fail at tau 1 shear stress. So this is failure shear stress we can say also. Okay. So this graph is called Mohr envelope, this line. So what is the meaning of this? Suppose you are here. What is the meaning of this? Suppose this is the normal. Suppose this is the sigma 2. Normal stress you kept, and shear stress up to reach, you have to reach up to tau 2. That is not touch this. That is below the Mohr envelope. It means soil will not fail. It means soil will not fail. So it means this is the area we can say this is the stable. If our sample is lying in between this area, below this Mohr envelope, that will be stable. Now, let's take a point somewhere else here. To see, you applied some normal stress sigma 3. So when you are increasing the shear stress, it will fail here. It will get fail here. Cannot reach here. And suppose directly you have applied some shear stress of value this, the soil will be not stable. It will get fail. Right? So this is the area for unstable. Now you can check the option. Mohr circle state of stress lies below in this area, below the Mohr envelope of soil. Soil will be unstable for that state of stress. No, this is suppose it is it is lying below this Mohr envelope. It will be stable. So this statement is not correct. This is false. Okay. Thank you. In the next lecture, I will also discuss some more numericals problem, more get previous year question from the shear strength of soil. So thank you.